I posted the lectures from the last 2 days on YouTube. I posted the next project assignment. Let's take a look at that really quick if I can. Okay, so I need to publish this schedule online, and homework one is due, what is that, tomorrow? And then I haven't posted these homeworks, so I'll post them, I'll move them out a little bit. The homeworks are not intended to take all that much time, just give me some reasonable answers about the questions. So I'll get those posted. I posted the P2, the background, moved it, the dates. I moved the dates for the other things down. The original schedule called those S1, S2, S3. Now it's P1, P2, P3 to be consistent with the project assignment notation. I also provided a description in the rubric about what you should be including in the background. Basically, it should be anything that somebody needs to know to understand what you're doing. Which means generally, if you're experimenting with a real world situation, then you want to describe the real world problem or issue that you're trying to address. You don't. You have a purely artificial construct that you're dealing with. So you can just describe the what you're seeing in the literature as far as what a fuzzy cognitive map is, how's it built, that kind of thing. Then because that's the quote real world thing, then you're going to model that. Then you may want to throw in, like they do, here's some simple examples. Right. And they try to tie them to real world stuff, as you've noticed, like a lot they're really thrilled about drug interdiction for some reason. But you don't even have to do that. You can just say, look, here's a graph with 3 nodes. We don't care what they mean, but they have this relationship. Okay. You've got some interesting work to do to get the biology of what's happening in the real world, right? So that's that. Then, since you guys have real world stuff that you're trying to model, you may want to incorporate some other people's models. Look, here's some ways that people try to model this, and you kind of put a menu in there. You may only do one, you may do three, it depends on what you need to say. Generally, you put in a really high level description of a couple, and then you'll say, I'm not going to go with this one because, or I'm going to use this approach, but I'm going to steal from this other person's approach, and I'm going to steal from this other person's approach and put it together. And here's why, because the things that I need to address in my simulation are different from what they needed to address in their experiment, and therefore I can use part of what they are doing, but I don't need it all. You do not need to put your model in here, your model, but you might. You might. Um, you don't need to put that in this deliverable. If you have one ready, that's great. Now the model for you, the stuff that's always tough uh, for you, doing the UAVs can be easy because they can be, point masses in a vacuum. It's, the classic physics problem. The harder part is the environment, the skyways or whatever. Yeah. For the robot with the mass, though, with the stability, that's a little tougher. Then you have to model. Actually, it can't just be a point mass in a vacuum. If you're actually interested in trying to develop robot stability software, you have to model the physics of how that UAV moves. So that's all up there. If you have questions, then let me know. And I want to devote probably a larger portion of the time tomorrow towards going one-on-one with you guys and answering your questions and helping you prep for the writing or review any draft material that you have or any of the source material that you have. All right. So These notes are summarized from notes that Dr. Sean Dougherty of Human Factors has. The Human Factors people, they're very interested in the design of experiments because they are trying to assess what makes a good or a bad design from a human factors standpoint. And really, the only way you can assess that is take humans and run them through some kind of test. So they do, I guess that department used to be called Human Factors in Psychology. It's something slightly different than that now. But they are doing all kinds of experiments, or are at least interested in all kinds of experiments about how do humans perceive the environment around them, and how do they take in information, and how do they respond to information. So for example, a number of years ago, 15-ish, 12-ish, I was involved with an experiment over at the Florida test bed. You know, Embry-Riddle has a very high quality FAA level, FAA sanctified test bed where we can simulate basically global aerospace. And we were putting real live, honest to gosh air traffic controllers that the FAA supplied to us and putting them in a simulated environment where they were doing some controlling of flights through metering service. It wasn't like where they were landing or taking off. They were just getting them through an area, right? So here's the area, here's the flights, blah, blah, blah. And we basically threw simulated events at them. And the FAA studies that kind of thing all the time. How do they process the information? How do they plan ahead? So normally during normal traffic flow and not a heavy workload, an air traffic controller has a plan for what they're going to do with each flight, right? They make initial contact with the flight. They know what that flight's intentions are. They find out what that flight's intentions are. And then they're able to say, okay, I'm going to put this flight here, this one here, this one here, and they can plan several moves ahead. When the load gets too heavy, that breaks down. And they're just like they go into a reactive mode instead of a deliberative mode. And so they're like, oh my God, I got to separate these two planes so they don't crash, right? So the FAA likes to study things like how much workload is too much workload? When do they go from the deliberative case to the reactive case? Those kinds of things. How much stress can you put on these people and they can still function and do their job? So these are experiments. You have to do the experiments because you can't just come up with a formula and say, this is how people behave, right? We also, of course, do experiments in the case of like what Alex is doing. Alex is developing policy, basically, right? So a lot of people are doing experiments about, hey, how do UAVs all, you know, once we fill the sky with UAVs, how do we do it in a reasonable way? How do we make sure that in mixed airspace, unmanned and manned or staffed and unstaffed vehicles can play nicely together? That's policy development, right? So we do a lot of experiments for that. Part of the test, part of the test that they did over in the test bed, the Florida test bed, a few years ago, were things like a specific airline wanted to have their flights that were incoming be prioritized in a specific way. They basically prioritized their flights in such a way that the most number of flights went to the gate on time, and they have a really weird definition of on time, like you can be X number of minutes late and you're still on time. Which meant that while the planes were coming in, the software was going to recommend to the air traffic controllers which ones they would position first in line and which ones they would tell, hey, you need to slow down and you're going to go behind this other flight. At the same time, it's an interesting problem because at the same time, that was one airline's preference, but you were not allowed to affect the other airlines. In other words, you couldn't give Delta priority over everybody else because that's not fair to everybody else. So they developed software for that. And then they did experiments that were not involving human air traffic controllers, just to show that the software could actually perform this prioritization task and not affect the other airlines. It's not something that you can easily come up with a formula for and say, oh, here's the answer. So what do? You do experiments. We do experiments to try to develop causation. This is the classic thing, right? Well, why do you do variables and change the variable values? You're trying to determine the effect of a variable change on a result. That's causation. And you may have heard the term, correlation is not causation. Just because one thing follows another does not mean that the first thing caused the second. And so what experimentation is trying to do is trying to actually determine the causation. Did this event actually cause something? Or did this value of this experimental variable have an effect on the system? We experiment to understand things. So you'll see people come up with models for how galaxies formed, and then how can you do an experiment on that? Well, you can't actually create your own galaxy. Oh, except in the simulated world, you can actually have many, 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 many particles all interacting with each other and see how they form. Do they form star clusters? Do they form galaxies? That kind of thing. And clearly that's not something, and that's not an experiment that you can't just go out in the real world and follow these things. The time scales are wrong, for one thing, right? Billions of years. We don't have time to wait for that. So instead, you come up with a hypothesis and you come up with a really good fast computer, and then do these heavy computational load experiments. The classic experimental form, as you guys I'm sure know from your probably Physics 1 class, and probably from high school too, is right, here's a variable, change one variable and value at a time, and you watch the effect of that variable change as you watch the effect of the output, right? The effect of that variable change on the output of the system, whatever the output is that you're measuring. I'll pause here and take a quick side trip. We're going to talk a little bit, not much, about statistics later on, because in order for this to make any sense, you actually do have to frame things in a statistical way. If you notice how people frame things that know what they're talking about, or they're not just acting colloquially, they frame things in a very specific way that allows for the statistical likelihood of something happening. So when we talk about causation, we generally, colloquially, if we're just out on the street talking to other people, we're like, smoking causes cancer. Okay, and that's an acceptable statement, right, when you're outside of the lab. But read the package on the side of the cigarettes. Right? The real thing is, smoking is correlated with a causation of cancer, meaning that if you smoke, you're not absolutely 100% going to get cancer, right? Smoking causes cancer means you smoke, you're going to get cancer, right? What it really means is there is a statistically higher likelihood. That's what that means. And so everything that we do in the experimentation world does end up getting framed as a experimentally likely, a statistically likely kind of thing, which means that we have to delve into statistics just enough to understand how to process the data and frame the question. Basically, what the people in the statistics world have decided, well, let's go backwards just a second. One basic way to understand statistics is you're always trying to answer this one question. And the one question is it the same? Classic statistics problem or combinatorics problem. I've got a barrel full of white and black marbles, right? And I pull some out, and some of them are white and some of them are black, right? So I've got a barrel full of white and black marbles, and you pull some out, and some are white and some are black. Then you put them all back in, and we're going to take the barrel out of the room, and we have an identical barrel, but it's got a different mixture of white and black marbles in it, okay? So we bring a barrel back in the room, and the question is, did I bring the same barrel back in, or did I bring the new barrel back in? Did I swap them out? And the only really way you can answer that is to look at all the marbles, right? To count all the black and white marbles. But that's generally not feasible. So what do? You pull a sample out of the barrel that came back in and you try to make an estimate. Well, gosh, is the number of black and white marbles that I pulled out this time so different that it's probably not the same barrel? Now, notice what you can't say. You can't say this is definitely not the same barrel, right? All you can say is it's probably not the same barrel. If I bring the first barrel in and you pull out 10 marbles and they're all white, and then I go and go it out and bring in the other one, you pull out 10 marbles and they're all black. It's tempting to say these are not the same barrel, right? The first one I got all white, the second one I got all black. Clearly they're not the same. You can't say that. All you can say it is statistically unlikely that these are the same barrels. That's all you could say. And the way I can cheat the system, by the way, let's say I had a 50-50 white-black marble mix. If I put all the white marbles on top of all the black marbles and you pulled out 10 white ones, then I took the barrel out and swapped it so all the black ones are on top, you pulled out 10 black ones, it's the same barrel, but you just happen to pull out the wrong, different colors based on my manipulation. You can also get those same effects. It's statistically unlikely, but it's possible if the black and white marbles are all mixed up. Okay. So what are you trying to do? You're trying to figure out causation, but generally, almost everything has a violation of the rule. Generally, you can't say, aha, this is the best policy or this is the effect of the thing. Normally, what you can say is, it is statistically likely that. Right? And the standard, you guys have taken statistics? I think most or all of you have, and you had the Z. Oh yeah, the Z thing. What was that about? That's a way for them to use tables for pre-solved values of the bell curve. And what you were looking for was basically that if you saw that there was an effect, you do some kind of an experiment, you change your variable of interest, you saw a different result, and if you could verify through your statistics that new result, that there was a less than 5% chance that it was just you got lucky, right? That it was, look, it could be that this new result was an aberration, right? It could be that by changing the variable, the system output actually didn't change at all, but you just statistically got unlucky with some results, right? So if you can say there's only a 5% or less chance that your new result was obtained by luck, basically, then that's enough in the statistics world to say, okay, we can claim that this variable change really did cause the output change. In other words, again, with experimentation, you're going to change the variable, you're going to change the value. You may change it, again, we tend to think in terms of low and high. You'll see why in a minute. You have a low value for your experimental variable. You have a high value for your experimental variable. You might run both of those cases 100 times and average the results. Why do you do it 100 times? Generally, you're dealing with a system that is not determinate, so you're going to get different results each time you do a run of a scenario. And so you have to do them multiple times and average the results, okay? Then you say, okay, now based on the averages results, I'm looking at these differences. I've got a bell curve. There's less than a 5% chance that these differences are just randomness, random noise. There's less than a 5% chance. So there's a 95% chance that the change in my variable actually did cause the result. Now, where did that 5% come from? Somebody just, seriously, like 150 years ago, somebody just grabbed it out of the air and everyone's like, hey, that sounds good. 5% sounds good. Now, as you know, you can pick any value you really like. If you want to go to a 1% value, you can do that. But generally, all of those tables that you've worked with in statistics class were set up for generally for a 5%. So that's what the classic experiments are. You have a variable, you have a situation that is so complex that it is not a deterministic result. If it was, you probably didn't need a simulation. If it was, you could probably build a model and do the calculations and get your result. So instead, what do? You do a low level for your experiment for your experimental variable, run it multiple times, average the results. High level, run it multiple times, average the results. As you might guess, there's plenty of room for people to argue with you on all of these things. How many times did you run your experiment? 10 times. That's not enough. I don't know, maybe it is enough. But people can argue that, right? So how many times you can run? 100 times. So now people start to worry about, and again, you talked about this in statistics class, your sample size, right? What's a good sample size? That kind of thing. So your sample size here might be how many experimental runs did you do on a single scenario. Most of you guys are in a place where you four are all going to be in a place where for the same initial starting conditions, you probably will get variations on your results because you're going to have randomness involved in your simulations. Yours, if you have a fully deterministic system, it'll always give you the same result. But since you're allowing nodes to do interesting things, you may make nodes that are decision makers that have some randomness in them, and then you won't get the same results all the time. Okay. Clear on that? It's a lot of, I think, hopefully mostly review, but some of this is review from stuff you've seen like 6 or 7 years ago. So, and framed a little differently, I think, too. Okay. So, generally, experiment variables are placed in these different categories. Independent, that's the one that you are, that's the variable that you're interested in. Now, unfortunately, or fortunately, a lot of times we're not interested in a single experimental variable. We're interested in multiple ones. So, for example, your motorcycles driving down the highway with autonomous vehicles, you can have low density traffic cases and high density traffic cases. And then you can have relatively well-behaved motorcyclists and really crazy motorcyclists. And then you can have low density of motorcyclists, high density of motorcyclists, right? What happens during bike week, right? So you've got mechanisms where you can develop different kinds of variables, each of which then can become independent variables that you want to manipulate. The dependent is the stuff that you're looking for, the output. So again, I think output for you two might be the number of safety incursions there were, that kind of thing. Output for your robot might be how stable it was, how long, what's the average length of time that it remains stable, or things like that. Or if you're doing room mapping, what is the total time it took for the room mapping, right? Those kinds of things. Extraneous, all the things that could be independent, but you're assuming, and notice the assumption there, you're assuming that there don't cares. So you probably, they may be features of your model, features of your simulation because they're needed to run the simulation, but you're probably not going to play the high-low game with them because in theory, what you're saying is it doesn't matter. So if it doesn't matter, why do extra scenarios? By the way, you may run, so we'll talk about that in a little bit. You may do some screening tests early on to try to weed out some variables. You might say to yourself, I don't know if this variable has an effect or not. How can you find out? Run a simple screening scenario. See if it does. Confounding variables, anything that could provide alternate explanations for the results. So again, what we're assuming is, oh, we had low and high values for an experimental variable, and we had some kind of output 1 and output 2. And so we're claiming that the low and high was the thing that caused this result to change. It may be that there was something else happening. It may be that even by incorporating the low and high for your experimental value, you had to incorporate some other things, and those other things were actually the ones that were the foundation of the causation. And then controlled everything that you're able to keep constant during the experiment. So in a specific scenario or case, you might have, let's say you have two variables of interest. They're independent, each of which could be low and high. But if I only, variable A and variable B, but if I take variable A low and variable B low, and then I take variable A high and variable B stays low, at least during that one scenario or that pairing of scenarios, we're going to say that we controlled B, right? We kept it the same. So basically, anything that you're able to nail down. And why are you trying to nail it down? You're trying to nail it down so that you can truly identify, oh, this variable that I'm modifying really did cause this effect to a statistically likely degree. Okay, I think I have some notes here. So how do you identify the confounding variables? You guys are doing this now. This is one of the reasons you do a background section is for your own, it's for your own education so that you are knowledgeable enough to do the simulation that you're trying to do. You're presenting the background material for the reader, but really what you're doing is getting up to speed on the topic and finding out what have other people done and what traps are there. It is pretty normal in a graduate program, if you're going to do a significant amount of research, for the first thing you do is you actually submit a research proposal, and the bulk of that research proposal is about doing a literature search where you're just proving to the professor that's going to be your advisor, yeah, I know enough about this where I know what I'm talking about. And so I'm equipped to go forward with my research. Within our grad programs at the master's level, we have master's thesis. So you have to present a thesis proposal. And if we don't do thesis, we have a class called Graduate Research Project, which requires a proposal. To get your PhD dissertation, you have to put in a proposal, right? And again, all of those things, a lot of that is about the research, the literature search. So by doing the literature search, what you hopefully will encounter is if there are confounding variables out there, that will be noted in the literature. And then your overall design type of the experiment. This is not so much the design type of the simulation, the design type of the experiment. How are you setting up your dependent and independent, right? So between subject or within subject. So here's how that works. Between subject, the psych people, you've heard about these cases a lot, or a basic survey result. We surveyed 1,000 people, and here's what they told us. Well, that's 1,000 different people, right? So they have, it would be a between subject survey. If you wanted to study the impact of how to frame a question, let's say, and people who do surveys study this all the time. So you can ask a question one way, and we're going to ask 1,000 people. We're going to ask a question another way. We're going to ask 1,000 people. That would be a better example, right? The variable of interest is how did you change the question, or how did you frame the question? How does that affect the result? And so by asking that question two different ways, then you're trying to measure, did you get a different response from people? But you're doing it between subjects, right? You didn't ask the same person the same question two different ways. You asked different people the question two different ways. And people who are doing political polling particularly are like it there's so many levels of chicanery and correctness and accidental and so, sometimes purposeful and sometimes accidental fudging of the results just by how the questions are framed. And then there's also, there was a famous case back when John McCain was running in 2008 where the poll isn't really a poll. The poll, they call it a push poll. The poll is there to try to convince you not to vote for the candidate. So there was a case, and they're running their primaries in 2008. John McCain looks like he's going to do really well in the South Carolina primary. And all of a sudden, this poll comes out in South Carolina primary that says, would you vote for him if you knew he had a black illegitimate baby? It wasn't true, right? And they reframed it as, would you vote for this guy? But then everybody's like, oh, I'm not voting for that guy. He's got a black illegitimate baby. And he didn't do so well in the primary. That's a famous example of how those things can be manipulated. But people who do legitimate polling and honest, they're actually trying to get results for their customers, still have to worry about how did we frame the question. You mostly hear about polling from a political standpoint, but as you might suspect, product people are huge on polling. Hey, if I package it this way versus that way, right? If I've added this, here's two different ways we might make our potato chips. The flavors are slightly different here. Try them, see what you think. Those kinds of things. So there are polling companies that are working for industry. Questions? Okay, so you're going to design your model, you're going to design your simulation, and then you're going to design your experiment. And your experiment is going to be a series of simulations, a series of scenarios, I should say, where a scenario is basically you're setting up the environment, you're setting up the conditions, you're setting up all the initial conditions. So if we have the classic Boyd's model, the scenario would be, how many Boyds do I have? And then what are the weights of the relative of the three vectors that we create? What are their relative weights when we combine them? How big is the visibility radius? Right? You can play with all of those variables. Each one of them would be a scenario. And then for each scenario, you might run it 10 times, 20 times, 50 times, something like that, and then average the results. Which means one of the things that can be difficult with simulations that's initially overlooked until you start to deal with the problem is, you have to have a data plan, right? You have to have an idea of, how am I going to store this data? So it's kind of, I'm saying that you create a model and then you create a simulation and then you create an experiment. All three of those are so closely tied together that each one really is affecting the other. So you kind of start out not with a specific experiment plan, but you start out with your basic research questions, which is why I asked you to produce those really early on in the course. Because once you do that, it forces you down the path of, okay, now that I have this research question, how might I try to answer it? And you can get a notional idea. You don't have to have a 100% firm idea, but a notional idea of how you're going to do the experiments, how you're going to do your simulation runs, which then tells you, what do you need to build into your model and what can you leave out? What do you need to build into your simulation and what can you leave out? The idea here, this stuff started in the 1600s, got formalized in the 1800s, but a lot of this came out post-World War II, and I'm noting here, improving the efficiency and quality of the industrial products. You may have heard of a person called Deming. Anybody take an industrial, do we have industrial engineering classes here? I don't think we do. the business school may have something relates to it, and our systems people might have touched on the topic. But basically what the Deming was doing was saying, look, you've got a factory, it's creating product. It's probably not as efficient as it could be, and the product is probably not as good as it could be. So what you can do is just keep track of everything, keep track of throughput rates, keep track of, how often employees get injured, keep track of your quality of, how often do you fail a quality check, these kinds of things. And then make a change somewhere in your process in the factory and see what happens. And then if it works, keep it, right? If not, back off and make another change and make another change. And so it's basically an evolutionary approach, right? Where you're very slowly trying to incrementally improve the process of manufacturing. And the Americans, he presented this to the Americans, and of course, post-World War II America, business was booming. We were the only unbombed major manufacturer in the world. So we were happy as ducks making stuff like crazy and selling to the rest of the world, which was trying to rebuild. And so our design, our model of improvement wasn't so much incremental. It was more like you had this radical shift, like, Ford created the moving production line, right? That was a radical shift. So Deming sold his ideas or took his ideas abroad, and the Japanese really picked up on it. And within 30 years, they were outselling the US. That's when the US car market really tanked in the 70s and 80s, because all of a sudden Toyota and Honda were producing these cars that could go, 200, 300,000 miles, and American cars fell apart after 2 years. So that's where you can see that stuff. There's a lot of this stuff in industrial engineering that you can go steal if you have the time to read up on these things. Experimental psychology and human factors also did that. As I said, the psychology people, they love to do experiments on people. And they did some really famous unethical ones that led to the rise of the IRBs, right? The famous Milgram experiment, or the Stanford prisoner experiment, right? Famous things that were really abusive towards people. But they also developed, here's how you can do some experimentation and the statistical analysis to try to determine cause and effect. Like I said earlier, psychologists, when they're doing experiments with you, they love to lie to you, right? They love to tell you this is the experiment, but it's actually not the experiment. Has anyone taken like a Psych 101 class? Remember the one where you say, you get a bunch of people in the room and there's lines on a chart, and you have to ask someone, which is the longest line? So we say, which is the longest line? And so you can see what the longest line is. But then these guys are all part of the experiment. And I say, which is the longest line? And you pick one that's not the longest, not the longest, not the longest, not the longest. Now we go to you and we see how much did peer pressure affect you. Do you pick the one that's clearly the longest, or do you say the one that they said?
I'm an a-hole. I'll ask them, are y'all stupid?
Yeah, that one. So, but it gives you an idea of, this is how psychologists tend to their classic psychology experiment. Another famous one is they'll say, okay, they always give like $10 to undergrad students to do these tests, right? So, okay, so you come in a room and you wait here in this room, and we'll call you in to do the experiment. And then there's a bunch of people in the room waiting to be called in, like you're like a waiting room in a doctor's office. And then smoke starts coming out from one of the doors, underneath one of the doors. And everybody else who's already in on the experiment sits there really calmly and keeps reading their magazines. And then the idea is, does the person react to the smoke or not? So again, they're lying to you. The experiment is sitting in the waiting room and having, again, peer pressure. I told you with the experiments we did at UCF, we were having robotic cars that either performed well or performed poorly in a maze, and it was nothing at all about an actual autonomous robot. It was Wizard of Oz with somebody radio controlling the car. Right? Anyway, be aware. Just be aware. if the site people want to do an experiment on you while you're here and give you $10 or whatever they do, look for what they're really doing. Because whatever they tell you they're doing, maybe not. I also worked with some people called experimental economists, and they pride themselves on not lying to people and just telling people right out, here's the experiment. And in order to get good results, they use real money. So they're like, look, you can really get $100 out of this experiment. Anyway, be aware that there's a long history of this. The whole premise, of course, is that you can identify some experimental variable that you're interested in, and then through modification of that variable or variables, try to find out some cause and effect. Things get difficult, as we'll see in a little bit, when you have multiple variables that you can play around with. Okay, so classical experiment design is where you change one variable at a time. So you say, I've got 3 variables and I arbitrarily assign a value of low and high to each one. And so I'm going to run my experiments as low, 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 high, low, high, low, right? You're doing one at a time. Any issues with that? So a couple things could go wrong, right? A couple things go wrong. One is the most obvious 2 problems that show up. Number one, if you have very many variables, you have a combinatorial explosion in the permutations of high, low, high. Okay. It's 2 to the n, where n is the number of variables. So if I have 3 variables, I've got 8 test cases, each of which you may have to run multiple times. If I've got 4 variables, I've got 16 test cases. If I've got 5 variables, I've got 32 test cases. 10 variables, 1,024 test cases. It's a combinatorial explosion. So it becomes not feasible, unfeasible to run every possible combination. And that kind of doubling problem, that 2 to the n problem, shows up a fair amount in computer science, and we call those unfeasible problems. So that's the first thing. The second major thing is that you are looking at one variable change at a time. As I've put in the notes here, sometimes things are actually going together. And so the effects of 2 variables operating together is really where you're going to get a change. In aircraft safety, when they talk about, what's that show? There's a show all about airplane crashes. What's that thing called? Air disasters or something like that, or whatever it is. And they talk about like chain of causation for these crashes. And it's never just one thing. The reason it's called a chain of causation is because it's one thing followed by another thing, followed by another thing. And in each one of these things, the process that eventually led to the disaster could have stopped. But basically, these multiple variables were happening at the same time. The pilot was distracted because, I don't know, coffee got spilled in the lap at the same time that something else happened, at the same time that something else happened, right? So if you look at how disasters tend to occur, yeah, there's like a point of no return. But if you back up, there's usually several things happening, either in sequence or at the same time, that cause the issue. So you have to pull that into a if you just do the classic experiment design where you're changing one variable at a time, you may miss some interesting interactions between the variables. Okay, full factorial design is, like I said earlier, you take the arbitrary high-low of each variable. Oh, by the way, the third thing that can go wrong here, I mentioned the two obvious ones, but the third thing that can go wrong here is your values of high and low may not be sufficient to actually generate a change. That's fairly easy to get around. You can do some initial screening tests to try to figure out what is a big enough separation between high and low before I start to see some results. Now I'm sticking with high and low here. There are times when you might have, say, a single variable of interest and you're looking for like a breakpoint in behavior. So you may, instead of just having high, low, you may have gradations of values. That's a potential thing, right? All of these things are speaking to general cases. We can almost always create cases where we violate this rule, right? So instead of, again, if we go back to your traffic, you may have high-low traffic density, but maybe you don't. Maybe you have low, medium, high, and high, right? And maybe there's an interesting breakpoint in there that you can find that way. I remember reading somewhere years ago that on like an interstate system, right, a long straight or a long road without intersections, other than the very controlled way that you do entrance and egress through ramps, having a low density rate of traffic flows fine. And then as you start to increase traffic rate, the people that were doing the research found that there was a peak, if I remember right, there was a peak where the traffic rate started to go down a little bit, but then as you got higher, it actually increased again. The flow of traffic increased again, the efficiency, or however they measured it. And this was surprising to the researchers. And so they were trying to figure out why. But the point was they did an incremental increase, and what they were finding were interesting behaviors along the way. Now, what happened though at that high density, even though it started out efficiency, once they had injected some kind of an event, like somebody, put on their taillights or something, at the high density, that effect of that event was worse, created the backup wave than at the low density, which again is intuitive. But when everything was going fine, the traffic really was not that affected by the traffic density. And I think, if you drive on I-4, you can see that effect, right? You can drive on I-4 up here, it's not very full, and people go pretty quick. And then you go down into the middle of Orlando, and people are like butt to butt, and they're still going pretty quick. You got to be awake.
Well, why though, if something happens, that's why it shuts down.
Exactly, because now there's no room for anybody to have any accommodation for the event, right? I've only been to New York City one time, and another person was driving, and they were driving like, I don't know, they were this close to the car in front of them the whole time, but everybody was, and traffic was just moving like crazy. But yeah, if anything happened, there's no room for correction, right? There's no room for recovery. So yeah. So full factorial design, basically we're looking at a high-low, and then you get the 2 to the n test. So if you have very many factors that you're dealing with, very many experimental variables, then you're going to go into a partial factorial design. You may pick what you suspect are the key variables, or well, in this case, right. So in this case, we're definitely leaving some cases out. So again, you may pick what you think are going to be the most interesting cases. Now, the good news with that is if you have a really good understanding of the system, an intuitive understanding of the system, then you're probably being efficient and you're probably making good decisions. But again, the word is probably. So one of the things that happens with human intuitions is we're often wrong. And so how could you do a better job of trying to identify which of these variables are actually important? That's what screening is about. So you can imagine that you might do in a fairly complex simulation system, you can imagine that if the actual execution of the scenarios are expensive, say in terms of time and effort, you might do screening first to try to identify what variables are the most interesting to play with, what values make sense to play with. And quite frankly, you guys are going to kind of do this anyway, in the sense that as you're building out your simulation model, as you're actually implementing it, you're going to check it as you go, right? And so you're going to start playing around already. Before you get into the actual experiments, you're going to start playing around with your software, playing around with your simulation just to see if it works. And while you're there, you're probably going to start to get a sense of what variables are interesting to play with. Blocking, you do a series of experiments where you're modifying some of the variables, but you're holding the other ones fixed. Now, by doing that, it's another form of trying to tease out from the full factorial design what's important and what's not. But instead of playing with one variable at a time, you're going to do a series of experiments with multiple variables, and you're changing those multiple variables generally one at a time, and holding others constant. So the idea again is, let's say you think that I think these variables are of interest. I also think they have some interactions with each other, so I don't want to do it truly one at a time. I want to start to play around with these together, but I'll hold the other ones constant. I think these three are related, and these other four are not related to those, so I'll do these three and hold the other four constant. Then I might do another grouping where I change the other four and hold the first three constant. So I can do where I do blocking, where I can create multiple blocks of experiments. Now, the idea with your simulations in this class, we're on a short time frame. You're only one person. You're not a team of people, right? You have to put together the whole thing. So you may have an experiment design that has these elements, but it may be fairly simplistic, right? So maybe what you're going to do, you're going to identify all of your experimental variables. If they're small, you might just do a full factorial design and be done with it. If that's not feasible, you might just back off to, okay, I did some screening tests, and it looks like these three variables are the most important, so I'm going to do blocking where I only play with those three, but I don't change the others. Or okay, questions about how to compose. How are you going to compose your experiments? Like a top level, what are the variables that you're going to play with? What do we got?
The number of movements in airspace.
So it's like a density, right? All traveling in the same direction?
No, they'll have different routes.
Do you flag, like you had a number of safety violations or something like that was a metric. Is that basically somebody came within some radius of me?
Yeah, I'm gonna find actual numbers based on ConOps.
Will you play around with those, like have a small radius and a big radius?
Yeah, I could.
I mean, is that a variable of interest? How about the degree to which they're identical? Like, is everybody moving the same speed? Or do you have right? Do you have heterogeneous or homogeneous in terms of their speed? Right? Is that a variable of interest? I don't know.
Not sure yet.
Yeah. So
They won't be at different speeds.
I would think
In real life.
I would think in the real life they
but
may
in
be.
this, I can't make it like that. So it's
Yeah.
gonna be, I'm gonna have to pick things that are less important for this experiment. Here I'm more interested in policy, so I might just make policy speed.
It would be interesting though, even if they might want to, if they were alone, they would have different speeds they want to go at.
Yeah,
But since they're in a tightly packed corridor, just like on the highway, they may have to kind of get in line and go the same. They may converge to a single speed.
That's what I was different lanes
Mhm.
of it. You said they're going to different points. Are you putting those from different points at different elevations?
They're gonna be like origin and destination places, so like each, like in this case, I'm assuming that they're basically like EV tolls, right? And they'll take off from some origin. Some people have been playing with ideas of like vertiports or like different,
Like buses?
yeah, where they'll like take off and land. So I'll put a bunch of them within like 100-mile radius, and so I'll kind of randomly generate where they'll take off and where they might want to land, and then generate a route based off that. So each one will have their own route that they're flying.
But they're not constrained, like there's not a highway in the sky where if you, no matter where you take off, you have to get into this lane and then
There
go?
will be.
There will be,
I'm-
okay.
I'm going with the idea of.
Yeah.
Section. That's, I mean, it's unofficial, but if you look at any air travel, there's actual like corridors.
Yeah.
Yeah, I know.
They do see helicopters.
That's what they're,
Helicopters
yeah.
operate.
So with that, you need altitude delineation for direction. If you're going off with a human one for the corridors, you have altitude delineation. Like if you want to fly close to DC, which only like certain military helicopters can. You want to travel southbound because that's the best view, because that's where the route go lowest.
Gotcha.
So things like that, anyways, so for your corridors. And you said merge points, but you also need to have, split points.
Oh, like where they,
Yeah.
Because as crazy as sometimes something turning in front of you is way more, it increases the likelihood of actually hitting them. Because nobody's gonna fly, as the corridor is gonna be arranged, you're not gonna have a perfect line.
Yeah.
Like, with drones, so.
Mhm.
It's just it's one of those things that people don't think about, but it's actually very important in aviation, because when you turn, you bleed off forward velocity very quickly.
Gotcha. And then do you know, like for corridors, depending on the direction, do you know if they like determine that based off of altitude, like those helicopters flying at the lower altitude go this way, high altitude go the other way?
Yes,
That's how we do it.
yes, it's altitude. It's usually only about 1,000-foot difference, but you're supposed to stay at 1,000 feet. They're supposed to stay at 2,000 feet. That gives you, 500 meters or 500 feet separation.
To go like opposite directions.
Yeah, and that's for up in the sky, and for helicopters, it can get all the way down to 50. It would be.
So
That's probably what I'm working with, is more.
the number of merge points and split points may be a factor, right?
Yeah.
That might be a high-low variable. Right, so you can have density, how long is the corridor versus how many times does it split and merge? How wide do you separate, right? How much do you separate vertically between the directions? How wide do you make the corridor? Things like that.
The other thing with an air mobility question is the most dangerous time in a helicopter is takeoff and landing, because you're slow, you have less altitude, and you can't, so you can't. So how can a air mobility handle that? Do they climb in a spiral because they can operate like helicopters? Do they take off and they fly up to altitude above 1,000 feet, then they descend down in a spiral, or do they do an approach? Like, once you start doing approaches, you end up running into a whole entire problems of people who are going to complain about.
Yeah.
Right, yeah, then you get noise level. Stansbury is doing noise level along these corridors.
Yeah, that's an
interacting with the
interesting
environment.
problem. I think for this, that might be out of scope, because I'm assuming that the companies that make the EV tools are like, have this in mind. And I know some of them do, like we have Wisp, that's been working on this for like a long time, Wisp, sorry. And there's a bunch of other companies, so for this, I'm more interested in like the air operations, and I'm kind of leaving takeoff as a constant variable.
William, you're in a similar boat, but you're on the ground, so we don't have to worry about altitude. You're in a 2D space. But similar things, I would think number of intersections might be in something. Traffic density is still something. 2D road, 2-lane roads versus 4-lane roads. right? These are things that
Yeah.
that you need to put in, and then how do you model it? How do you model a 2-lane highway from a 4-lane highway? So that's a question that you're gonna, well, you said you're using the Sumo though, right?
Yeah.
So a lot of your background is gonna be explaining how that works, I think. So what variables can you think of at the top of your head though?
Well, I was honestly thinking about all traffic flowing in one direction. Like I said, this is my first time using Sumo, but I'd like to